I will be introducing our keynote speaker from breakthroughs at Bell Labs, DEC, and Stanford, and then commercializing the routing technology that became the internet. Len Bozak is a true pioneer who helped shape the modern internet and how it all works. And then he went to co-found Cisco. Today it's CEO XKL. He continues to innovate, making optical networking simpler, more reliable, and more accessible to operators worldwide. Please welcome Len, and thank you for joining us on the stage.
Thank you, Chris. Your kind introduction. I'll do what I can to get us back on schedule, but I suspect they'll give us a couple minutes grace if we need it. All right, let's get started. Now, some of you have actually looked at my slides and you might find them just a little busy. Well, yeah, there's a lot of data and, in there. I will not be reading them to you. I'll point out things that I think are important to the flow, and you'll thank me. The first thing, though, we're going to talk about a theme that's going to run throughout the talk, which is there are some fundamental limits that occur, mostly physics. Part of it seems to be sociology, but mostly physics. And we can't easily get around them at any given time. Sure, they're not hard walls, most of them, but with any given level of effort, they're pretty binding limits. First off, this theme, the theme for this nano, gray theme for this nano, includes 5G. So we're going to spend about half of our time talking about the mobile communications revolution and where we've gotten today. And finally, I can't resist a small forecast. All right, it's not a surprise to anyone in this room that IP has essentially taken over. Can you imagine giving a presentation to a room full of venture capitalists and you start out with the idea of delivering whatever idea you have, not over IP? I don't think that's going to give you a warm reception to get started. It gives you a big hill to climb, but pretty much if we sell it today, it's sold over IP. We've just about done it. I recall a time in the 80s where I was told quite clearly that this protocol was never going to go anywhere. It was too expensive and it was too weird. Okay then, here we go. That little diagram you see at the top of this slide is one that everybody here can draw, and we're talking about layer 1 today primarily. The limits are down at the bottom, and we'll give you a little better view of those as we go on. But first off, you have Mr. Shannon to thank for the ideas that in any given communications channel, there are fundamental limits, and you're never going to get past that. Okay, here we are. Next one is a little more practical. As you go to build these systems, you find there is, for any level of expenditure you care to make, a limit to how fast you can make the pins go. Copper traces still matter quite a lot to us, and we'll talk about that indirectly in a bit. Power, heat, the two friends and enemies of us all. So if you want to build a cellular telephone, and we'll talk about those limits in an amusing moment, there are limits. And then finally you get to our friends at the GPU world. Even if you set the knob at 11, there's only so much heat you can get out with air. We'll see how this goes. And finally, there's a bit of the so-called logistic adoption curve. As far as we know, every technology has gone through this. One suspects that wheels and axles had the same idea. You start with early adopters, there's the broad expansion phase, and finally a maturity. Here we go. Okay, this is a rather busy slide, and we're not going to dwell on every one of these things. But in that upper left-hand corner, there's some people in this room who might have even used one of those little wonders. It weighed the better part of a kilogram, and it gave you 10 minutes about of talk time. for something like, no, 30, yes, it gave you about 10 minutes of talk time for hours and hours of recharge time. We've done better. Decade by decade, that, by the way, is the organization of the slide. We started digital, CDMA in the US, GSM in Europe. That little Nokia candy bar phone there really was a tremendous advance. A few of you probably still have them in a desk drawer somewhere. Oh dear, the 2000s. It was the BlackBerry. Remember BlackBerries? It was an advance. It was the famous keyboard with the flying thumbs. You see that to this day. Important thing there in 2007. If you ever, I've read the FCC filing for it, and it started out to be an iPod Touch with a cellular modem. They gave it the name iPhone. Big change. In particular, well, we'll go on to the 2010s. The iPhone 8, one of the most produced complex objects the civilization has ever produced. In the high 80 millions of them, of that particular design, were made. The world changed with this type of human interface and this level of computes in your pocket. The 2020s, just recently. Well, I had a whole module on satellite stuff. I'm afraid we would truly run over if I went into that. But Starlink is spreading the IP world geographically, since in principle you can almost anywhere on the Earth's surface get Starlink service. Note with a little bit of amusement, it turns out that your cell phone actually can use an old-fashioned so-called bent pipe satellite. It's just that it's a lot of work. Apple undertook that work, and so they started to give you emergency services over satellite. It's not perfect. You have to see the sky. There's lots of things about it, but there's a little merger of the in-your-pocket cellular world and the satellite communications world. Now, underneath this, literally underneath this, sorry about that for folks in the back of the room, but giving you a sense of pace in the progress. The DEC Intel Xerox Ethernet was about done in 1980. That was the 10 megabit Ethernet over coax. And it took 15 years to get to 100 base T. Okay, well, I guess we're a little bit ahead. Notice down there in the bottom there, the 1988, the AGS Plus was the machine that my models predicted that we could network literally every computer then in existence. Sort of a milestone, thinking you might be done with IP at that point, at least in the sense of success. All right, the 90s. Crept ahead and gave you 100 base T, so we went a factor of 10 in 15 years. And the early days of Wi-Fi. It was a little bit eccentric, and it wasn't very popular at the time, I don't think. I actually had some 802.11 equipment, and it didn't work very well yet. All right, the 2000s. Well, okay. In 7 years, we picked up another factor of 10 in speed. We had some standard for 10 gigabit per second, and a very optimistic 10 gig base T, but that didn't take off for a little bit. So it took us 15 years to get one factor of 10, another 7 years for another factor of 10. And 2010s, we went to 100 gig Ethernet. That gave us 11 years for that factor of 10. Okay, we're starting to see a pace here. I'm not sure what I noted with, but in 2017, IPv6 finally was ratified by the IETF. Okay, a few of you are either grimacing or smiling. Okay, I won't try that again. The 2020s, we went in 7 years from 100 gig to 800. Well, there was 400, in only 4 years it went to 400 gig. And then another 3 years to 800 gig by spec. Now notice, everyone understands that having the spec finished doesn't mean the products are available. Indeed, there's a case to be made that 800 gig in small form factor pluggable is only conditionally available today. Okay, well, we're getting there though. And somebody's decided that a lot of this data came from the professional pundits, and somebody's decided that 2022 was the year that IP over WDM was a thing. Okay, fair enough. Somewhere in there it is. And that depended on the small form factor pluggables. Only last year we had Wi-Fi 7 released, and very specialized Ultra Ethernet. Ultra Ethernet is an attempt by the consortium to give some people an alternative to fiber channel at the very highest speeds. The folks training their AIs and not doing such a wonderful job in the computer science really find this important. Well, that was a core slide, wasn't it? Now let's talk about money. Everybody likes money. Cellular as a whole, mobile wireless, is a $250 billion a year business. All right then, I think you can call that a commercial success. What I should have called out here in the upper, there is a number above the upper right column there, and that is the total network spend, and it's $460 billion, almost $500 billion spent on the computer and communications network infrastructure and everything associated. Cellular is about half of it, and of that, half of it goes to the user segment, the stuff you carry around with you. And there's a reason why Samsung and Apple and Huawei are such big companies. That's where the money is, if you can go through the rigorous process of making those. Now, with this much money at stake, you might imagine that everybody who has any chance of taking some of it wants to have a say in how this network is built and run. And so the miracle isn't that or the observation isn't it's that it takes so long to do anything, it's that it makes progress at all. With that many competing voices, it's very hard to get anything like a consensus. But with all the standards bodies, with all the countries, with all the important politics of cellular spectrum allocation, we managed to make progress anyway, driven by $250 billion worth of fuel. So money does matter here. Now, the fun facts category, we now cover about 95% of the world's population. But that's really only about 15% of the land area. So our friends at Starlink have a place here to help get us to the rest of it. Okay, the mobile spend does indeed exceed this fixed line spend, but not commandingly. It's a 3% difference. And as you might expect, the guys who came most recently in Asia Pacific, they're doing the best. They have the best speeds and they're spending a lot of money just right now to improve their networks. Now, without spectrum, without allocated spectrum, you don't get an engineered network. So, assuming you want an engineered network, and I think that's what most people want in their pocket, it takes a lot of political will and a lot of industry help with the various governmental organizations. There's a table up there that tells you a bit about how much people were willing to pay per megahertz of spectrum. Well, it's not all the same value. And I think people can understand that the very low frequency stuff, well, there isn't that much of it, but it's really good for broad rural coverage. People were willing to pay $230 million per megahertz at auction. Now, you take a contrast there with the high band and millimeter wave. What's that, 2 million? But there's a whole lot of it. Unfortunately, the physics tells you you can't go very far with it, and it doesn't go through things very well. And so on we go. There's one anomaly about the mid 3.5 gig. It was very hard to do coordination with prior uses, so that people weren't too eager to use it. So let's talk about how the world has used this. Remember that logistic curve I showed you briefly? Well, you probably don't, but it starts slow, it rises fast, and then it levels out. Well, see that peak there in 2018? All right, that was the peak growth, and it's been slowing down ever since. But I point out, if you look at the left scale, it was basically 150% growth in 1 year. Okay, and now it's down to 20. But notice the units. I think the units of data there are exabytes. All right then, even a 20% growth is still a significant amount of stuff that needs to be present and used. Now, we talk about potential, and some of you may recall the somewhat marketing overreach about 5G when it wasn't here. These folks were really enthused, and I don't know whether to criticize them for being premature or just having let their enthusiasm get away with them. There was so much potential that they saw for these new technologies. And now that we see it, it was a significant development. It is widely deployed. It is a commercial and practical success. But as with so many things in life, it just didn't meet everyone's most optimistic hopes. And those were hopes. Those advertisements I saw were hopes. Again, you can offer, I understand there are other points of view about being less kind, but that's how I see it. Now, we're not done. 5G is still run in some sense, in some places, as a hybrid network, which does not give you the full advantage of the Wi-Fi potential. So when everything gets run in so-called standalone mode, that is 5G network native first, you get all of the improved sound quality, you get many possibilities that you just don't get otherwise. Now, we've pretty much succeeded in, and this was called enhanced mobile broadband. I'd have to say that that's pretty well done in most places. It's still expanding, coverage is still expanding, the network's still improving. But other things that people hoped for, less so. People were hoping that these systems could be used for literally everything. The Internet of Things networks, you name it, they were hopeful. Well, we're not really that far there. And then finally, you have the aspiration of ultra reliability with low latency. Well, look, physics tells you, if you're not close, it's going to take longer. Fine. But this really hasn't taken off. Now, I didn't realize it was so very close. The next property over is the AT&T Stadium. This is a great fun showcase for what the technology can do. They said, okay, we've got 105,000 seats. We're going to provision this network so that everybody can be watching the video feed of this game at the same time. Well, that's a pretty stiff spec. And so they put in hundreds and hundreds of equivalent cell sites. And the middle picture the second picture that shows you those little bubbles up there, those are what are called dielectric spot beam antennas. So to give you, adequately dense coverage, that's the sort of technology required. It wasn't just an ordinary antenna. The thing on the right is something I would dearly like to know more about, because I think the key to making this work is to have the content distribution nodes that are feeding all of those people their IP streams for the in-game come from that data center. So the bulk of the traffic would not even leave the stadium. I don't know whether that's actually true or not, but I certainly hope it is. It's quite an achievement, and it's right down the street. I thought about seeing whether we could organize a tour of at least the data center part, but never quite got there. A little bit of amusement here. Now, we have Wi-Fi data from the various stadia. Okay, here it goes, rising and rising. Whoops, we got a COVID divot. And then last year, we have a bit of an embarrassment. One of the streamers absolutely collapsed for half the game. Oops. We all try not to do that. All right, back to our through-line theme. .5G can use what's called 1024 QAM, that's 10 bits per symbol. And that gives you, in the spectrum available, potentially pretty high rates. It takes more power, but it does give you high density. Now, at least somewhere, you can walk around and get potentially 20 gig down and 10 gig up. Now, it may only be on one particular street corner in any given city, but you can, at least in theory, do it. The 5 millisecond latency target, I'm not sure how often we hit that. But it can be done. And that, of course, depends on the network engineering and the physics of where you're standing. Well, I tried to give you index numbers on power density. The modems have become tremendously more efficient. Unfortunately, the power amps, not so much. These advanced modulation techniques have a high peak to average ratio, and that means you need a pretty linear amp. And so they're not going to be improving in efficiency as long as we use these highly spectrally efficient techniques. And of course, then there's batteries. The big brick I showed you in the very first slide was NiCad batteries. They were heavy and they took forever to recharge. Your little lithium-ion batteries have tremendously improved power density, recharge fast, and unfortunately they have the bad habit of catching fire. Oh well, careful on that airplane. Now, the logistic curve, adoption, maturity, this is a mature technology. We have spread it around the world. It is commercially a fabulous success. Again, a $250 billion business, that's, as they say, not chopped liver. It still has room for tremendous growth, at least in terms of its details and scale. The broad advances are done. That's just true. And that is why we are, to a large extent, up on the top part of this curve. Okay. Sudden pivot, let's talk about Wi-Fi. It may surprise people, but 802.11b was from 1999. Well, I remember when it came out, but many in the room don't. It's been with us rather a long time. And I'm not going to go through the individual bubbles here, that would take us too long. But it expanded both in terms of modulation capacity. 802.11a actually started before B, but it came out a couple of years later. Then we kept improving modulation capacity. It got better at delivering the potential. You don't, just because a standard says you might do something, whether someone does it or not is a much more substantial and sometimes more difficult question. And Wi-Fi is intended to be, as the Brits say, cheap and cheerful. It's supposed to be inexpensive. It's supposed to be true that everyone can have some, but it's intended to be local. Okay, so as we run along here, generally speaking, modulation got better, a little more spectrum got allocated here and there, including the Wi-Fi 7 era where we got a nice dollop of 3 gigahertz spectrum. Being cheap and cheerful means that it's everywhere, so even the politicians get the message after a while. All right, the 6 gigahertz, anyway, the details are largely recited there. Most people who run these systems use a compromise between the very highest speeds and the very highest spectral efficiency. And now it's possible to build significant facility-wide Wi-Fi systems and deliver good results pretty uniformly. That's a significant advance. A little more than 30 years, but here we are. Now, how about money? Well, money matters. The units on the left of this slide are in millions. So notice that 20,000 million is 20 billion devices. These are actually things, the data here comes from people who have made and shipped chipsets. Now, it's possible that there's a vast warehouse full of chipsets somewhere holding them all, but I don't think so. Usually they get built into things and used. So I'm reasonably confident that there are billions and billions of these Wi-Fi devices. There is a sort of yellow-orange line that runs amongst all the green there, and those are by number the cumulative shipments for all the mobile devices that we believe were ever made. Might surprise you, Wi-Fi's outproduced the universal mobile technology. Well, it's important. Now, again, in the interest of time, we're not going to go into it too much, but the upper right-hand slide tells you, at least in an enterprise sense, something you probably already know. It's Cisco, well, now HP Enterprise, Ubiquiti, Huawei, and Juniper that are the folks who make up the bulk of the marketplace in terms of larger scale Wi-Fi. And that's who gets most of that market. All right. Now, where are we in terms of the technology assessment? They've gotten to 12 bits per symbol, or 4096 QAM, and that nice tasty bit of 6 gigahertz spectrum improves the reliability in a dense facility. Speed? Oh, somebody thinks they might get 46 gigabits per second, and I'm sure that within 20 feet of the access point you can do it, but it's like the 20 gigabits for our mobile friends. Yeah, you can do it, but it's not the way to bet. And obviously, depending on your user density and your access point density, you're either going to get better or worse latency and reliability. Power density matters a bit because these devices are on all the time. They're starting to be a noticeable worldwide power drain. And so as we've gotten better with sleep modes and things of that ilk, it continues to get better, but the more complex, the multiband radios and the more complex modulation schemes drive the specific power consumption up a little slower than the deep sleep modes and things like that is driving it down. So it looks like we've sort of plateaued in terms of global energy consumption for Wi-Fi. Again, I have to judge this as a pretty mature technology. The vast growth phases are over. There is plenty of it, and mostly what people are doing is improving it. All right. Now, something that people don't talk about as much as deserve, I think, the very first broadband network were cable TV systems. Yes, it started because some folks down in a valley in Pennsylvania wanted to get the big city football games and put an antenna up on the hill, but it went from there. This was the very first wide-scale broadband network, starting with analog television. And it's improved, decade by decade, digital, and now it's a hybrid fiber coax network, primarily delivering IP. Now, we're looking at some of the current and again, I'm not going to go into it in too great a detail. One of the things that they did is just about double the cable bandwidth, and they probably don't really want to try doing that again. There's just too many components that have to get changed each time. The world is pushing the actual fiber closer and closer to the consumer. In fact, it's happening in such a way that for greenfield construction, a number of cable companies have gotten a franchise agreement with a developer, and they put in essentially fiber to the home. Do we want to talk about? Okay, in terms of energy efficiency, it has gotten more energy efficient. That lower right-hand bar chart, though, goes in sort of its specific energy consumption. And it's basically kilowatt hours per terabyte delivered. I know it's an odd unit, but there it is. And so 3 to 5 times better performance happens with your fiber to the home networks. That's a pretty telling comparison. If you're building something new, everybody's putting in fiber. So here's a quick technology assessment. They're at 12 bits per symbol, and the practical limits of coax are, they can get 2 to 4 gigahertz because they're getting closer to the customer, but you have to keep changing too many devices. The connectors start to become fussy. Speed and latency, 10 gig down, 6 gig up. Once again, how many consumer computers are there that can consume 10 gigabits per second in a single node? So now you're talking about how many devices are going to operate at peaks simultaneously. That ought to do it. This no one can tell you that you need vastly more. Now, power has become a problem. The set-top boxes keep getting hotter, and the various other amplifiers and things are a significant power draw. And mature technology, yes, indeed. All right, we're going to go pretty quickly through bits about building your network. Well, what's it cost? Some pundits have told us that you can build a fiber network for about $100,000 a mile for underground fiber. And that might even be the actual direct contracted cost, but the pain of getting the permits and the right-of-ways You don't know whether the pain is financial or just institutional. And aerial fiber is less expensive. And with the modern dynamic dispersion compensation schemes, the fact that the fiber sways in the wind isn't so important as it once was. But it's basically how far do you want to go? That'll tell you how much you're going to spend. Let's not go into the details. Okay. Here comes AI. The graph on the left tells you about approximation of data center worldwide demand for power. And we're talking about terawatts, or terawatt hours per year, I suppose, same difference. And notice how, starting about 2023, the curves of the growth curve seems to keep going, but the actual data center part of it isn't growing so fast. And that difference is the entire, I'm not quite sure what to call it. AI is now everybody's slogan. It's their buzzword. And, well, there it is. Will we actually reach those growth projections? Well, the observation in the financial world is still apt here. No tree has ever grown to the sky. Don't know what's going to happen directly. Now let's talk about how we're doing in terms of power. Well, the answer is we're doing fabulously well, but we're not doing well enough. There you have 400, 800, an estimate for 1.6 terabits. The unit there is picojoules per bit, and you can figure out how that will bring you back to your package dissipation. But there's the breakdown between DSP drivers, the transconductance amplifiers, the lasers, and the power converters. Spare us from power converters. But we're doing better. From 400 to 1.6 terabits, factor of 4 in speed, but we didn't quite get the specific power down by a factor of 2. Kind of tells you it's got to take twice the power. All right then. And there's nothing you can do about that pretty much. What that means, no, I'm getting ahead of myself, sorry. All right, let's talk about where we are in our uniform assessment. We do see people running 64 QAM, 6-bit per symbol codes at 800 gig. If we expand from just the C band to the C and the L band, we get almost 12 terahertz worth of spectrum. Some number of you who are doing it realize that using both C and L band in the long haul sense is a pretty big change to your amp chains and the like, but it's still it's possible to do. More and more vendors are going to start offering that if they don't offer it today. And it's still going to be a problem, as you're going to see in a few minutes. We have something like pluggables at 800 gig. You know, our XKL owns several examples of these things. The good news is we actually can get a few of them. Notice that it's not yet send an order in and 6 weeks later you get your order. It's a little more constrained than that. Nor is it to the point where everybody's implementation is uniformly interoperable and equivalently performant. Still, we can easily see now the big frame fiber guys, if they don't actually have too many of them installed, they should be able to give you those big aluminum packaged 150 watt systems at 1.6 terahertz per color. All right, we're getting there. It's going to progress, but slower than we might imagine, and these fundamental limits are starting to actually bite. Okay. As you see from that I've just pointed out with our specific power consumption, it's improving, but not improving fast enough to take the actual per system power down. There we are. We've got room for growth, but the spectrum isn't infinite. 12 terahertz of bandwidth between the C and the L bands is not infinity. As we're starting to increase the spectral consumption, you'll start to notice as a system operator. All right, I promised that we would give you a little look ahead, and I could go on for rather a long time, which the clock tells me I only have a few minutes, so we'll stick at this. We're going to get 1.6 and 3.2 terabit per second pluggables. The 3.2 terahertz, I don't think we're prepared to say when. The 1.6, 5 years in terms of small form factor, but it shouldn't be the same package is my assessment. And 3.2 terahertz, you may be looking at 10 years. But I think it's going to be possible, but not in the same package you see today. They're going to be bigger, and you're going to have some more spectral congestion in your fiber. HFC, there's incremental progress to be had, but it's just a little better, and it's not going to be any sort of revolution. It's an important, big network, but it's not what people would build if you start from nothing today. It's fiber. Now, Wi-Fi. Okay, here comes Wi-Fi 8. We're not looking at capacity increases. We're not looking at peak speed increases. We're looking at procedural and software-oriented improvements that make the networks work better and, in a practical sense, deliver more. Well, that's the summary. Better latency most of the time. It's mature. It's getting better, but it's pretty well mature. And the hope is that by maintaining advances in power management, we're not going to burn down the world's residential power grids. 6G, there will be something that people call 6G. Although, in all honesty, if we manage to make 5G reach some of its potential, so-called 5.5G, that's a tremendous improvement in service to the world that is now without any reliable wireless. Maybe people have talked, because there's so much money involved, people fantasize about using this network as a way to drive the frontiers of radio forward. But once you get past tens of gigahertz, it starts to become a little impractical for people to just be around. So no one's confident how this is going to come out. And optics, well, we've tried optics for people walking around in a room, and it's hard. It's possible, but hard. And that terabit per second target you might have heard bandied about for 6G, well, somebody actually built a laboratory hero experiment that did very nearly that. But hero experiments are just that. Your fiber hero experiments of, hundreds and hundreds of terabits down one pair of fiber. Okay, as long as the right guy's in the room and nobody moves too much, that worked. That's not yet practical. Same thing here. Well, just the advances in IC technology are making the modem chips better. So you're going to get the potential of higher speeds at lower system power. Well, everybody welcomes the lower system power. That battery you carry around with you We'd like it all. Anybody want their cell phone to last less time? Show of hands. Okay, then. And what's driving this? All that money. There is just so much money here that people are desperate for any innovation that will let them expand their market. So far, the room echoes kind of with nothing. There's no big fundamental advance. It's mature. So here we are. We have a bit of time here at the end for questions. I'm happy to talk about anything you'd like. Please come up to the microphones. I think there are only 2 up front. I don't know if we have any rovers. And the organizers ask that you give an affiliation and your name and fire away. Yes, sir.
Hi, Brian Fields, Tampa Bay Access Exchange. I noticed you said that we're running out of bandwidth essentially on the fiber at some point in the L-band and C-band.
Yes, sir.
I was going to ask, one of the things I've been reading about some of the hollow core fiber is it appears to have like just almost unlimited bandwidth in terms of the wavelengths it can support. Is that anything? Okay,
hollow core is a nice advance. It gives you essentially free space propagation. It speeds up your propagation, it speeds propagation delay. And in the next few years, people should be starting to put more of it in. We don't quite have all the craft skills that we have for the good old SMF-28 class fiber. And that's the other problem. We have this worldwide infrastructure of existing fiber. If you're going to build something that depends upon hollow core fiber, it's a greenfield build. And here you have the problem that there's always somebody in your way. Trying to build an extensive greenfield network with all hollow core is quite a challenge. Sure, we've got technological potential there. Unfortunately, the limitations you run into, we've gotten a lot of things down about good old silica. What we don't have are extremely broadband optical amplifiers. We can cover the C-band with one rare earth doped fiber. We can cover the L-band with your choice of a couple different ones. Some people have tried high pump count Ramens. There are folks who will sell you a 6-pump Raman that does a credible job of covering both C and L-band, but it's, and by the way, your Raman gain in hollow core fiber is considerably lower. You don't get that lovely stimulated Raman inelastic scattering in essentially just air. Well, you can get it, but it's going to take a lot more power. So the different technologies associated with hollow core, we're not going to go there real soon, real far, and real fast. But it's there. I think it's going to have a useful place, but it's going to take longer than anybody believes.
Okay, thank you.
Thank you.
Hello, my name is Patrick Gilmore, and I'm representing Tigger. So you said that 3.2 is going to be much larger, it wouldn't fit in the same size and all this good stuff. Mm-hmm. I know very little of this compared to what you do, because since you do this for a living, but I am a little confused how you're predicting, 10 years out that we're not going to have, I don't know, 65K QAM and, sub-nanometer ASICs and whatever else it takes to make these things fit into the same form factor so we don't have to replace every piece of equipment we have today.
Okay, well, I happen to have sandbagged this funny you should ask. Okay, this little table of numbers is essentially we've now run off the edge of geek. The first two rows are things that now exist. And it gives you the nominal data rate, the modulation format now employed commonly, your so-called baud rate or symbol rate. Thank you, Claude Shannon. The optical bandwidth that it commonly takes to use that symbol rate. And now we talk about the user interface in terms of user lanes and the user data rate, the power and the process. The first two rows are what you see today. The last two rows, now let's look at a few things. Pretty commonly when you change from one line to the other, that's sort of one generation, you don't try and change everything at once. The actual practical pain of doing that is painful. And the customers feel that pain because there are things that go wrong in the development process. So notice you can see the modulation stayed the same between 400 and 800. The baud rate doubled, and that meant the bandwidth doubled. And so those 75 gigahertz channel filters you had at 400G have turned into 150 gigahertz channel filters at 800. Now, I point out to you that roughly speaking, that's 6 channels per terahertz, or maybe 30 channels per C-band or L-band, respectively. Half the number from the previous 400 gig generation. In order to stay in the same package, they doubled the data rate on each of those 8 lanes, and the power went from 20 watts to 30 watts. By the way, the 21 watts is still difficult to achieve. You can actually get a few with a finer IC process come out that give you a little better, but the 30 watts is still an aspirational goal. And those are built with the IC processes you see over there. Now let's talk about going to 1.6 terabits per second. If you don't want to cut the number of optical channels, you've got to improve the modulation. So you can go from QAM 16 or 4 bits per symbol to QAM 256 at 8 bits per symbol. The price, your A to D and D to A converters have to have higher performance, and you have to have some wider data paths in various places so the power in the DSP goes up. Okay, why 16 lanes? If you go talk to your board designers who are building the actual PC boards with 112 gigabit per second signals, they can do it. Well, they could do it at 400, they could do it at 800, and they do not exhibit a lot of confidence of the first try success if you went to 224. 224 exists. I have actually been near ICs operating at that rate. They're 3 nanometer ICs as a rule, which is, that's last year's process for people like Apple and Samsung, but it's still difficult. Now, I say that if you change your package, because I think you have to, because you're not going to get it done in 30 watts, and taking much more than 30 watts out of your QSFP or OSFP, maybe the OSFPs could do it, but the QSFP certainly can't, means you need a bigger package. It just needs to have more surface area, more metal, and my estimate is with all of those changes, it's going to burn 40 watts, 45 watts at better a 2 nanometer process. That's a more sure result. And there you're catching up to a lot of the cell phone guys. They're the ones driving the IC process world. So again, you'll notice the things that we changed were the modulation format. We didn't change the baud rate, the bandwidth. We added user lanes, but we didn't make them go faster. So it's probably a feasible generational change. But we burned 45 watts to do it. We probably can't get that back into making that work in 32 watts, nah, you need to make the knob go to 14 to make that work, and that just ain't happening. No, 3.2 terabits. We probably can't give you QAM 16K. So it's gonna get worse. So my hypothesis is we can manage QAM 1024, 10 bits per symbol, but that's gonna take 160 gigabaud. Okay, the reason the numbers come out to half the data rate you expect is because this is per polarization. There are two parallel polarization streams going down your fiber. But this would not require a package change. In other words, the idea is when you make the package change, don't do it every time, would you? So let's get used to it mechanically and all the rest. Same package, but you are going to have to go to your 224 gig signaling rate on the user side. And with a 1.4 nanometer process, I estimate this is going to take just a little shy of 70 watts. I don't see how this is, we can avoid this. If anybody wants to, if anyone has a better idea or you have something in the back lab that's doing better, oh, I'd be delighted. Please do come tell me about it. I'd be delighted. Anyway, have we any other additional questions? We've nominally, my clock says 0. So, all right, thank you all. Thank you.